Today, we're going to talk about our big application for a first semester calculus course, and that is velocity and acceleration. So hopefully you remember this graph from our first day of class when we're looking at my road trip, and we looked at this one snippet that was from hour 1 to hour 3. We had our distance in miles on the y-axis and hours on the x-axis. And we talked about our average rate of change, our average speed over this trip, which ended up being 50 miles per hour. So we essentially calculated the slope of the line between the beginning and the end. And we said we traveled 100 miles, divided that by our 2 hours, and got 50 miles per hour. And then we said that our goal this semester for looking at derivatives was to find rather instantaneous rates of change. So we said, like, we honed in on this point here, and we said what we really want is the slope of the tangent line, and that would give us our instantaneous rate of change. So our whole goal this semester was to get derivatives. So our derivative, which as we know well by now gives us our slope of our tangent line. But the whole reason we wanted that was because we wanted that instantaneous rate of change. So our instantaneous rate of change, in this case, that was the speed, the instantaneous speed at any given point on the trip. And what I said that was if we had a video of our speedometer, if we hit the pause button at that one particular instant, what would the speedometer say our speed was at that particular instant? All right, so this was our pause button look at the speedometer. And that's what we are going to tie back to the derivative. So when we have a function like the one on the previous slide, where you have distance on the vertical axis and time on the horizontal axis, we call this a position function. It gives you the distance or the displacement of an object over time. We conventionally use s to represent that position function, s of t. So we don't use x, we use t to stand for time. So if we have s of t being the function giving the position of an object at time t, then the velocity of the object at time t is given by the derivative of the position function. All right, and we use v of t for our velocity function. Now I use the word velocity instead of speed deliberately. Up until this point, speed and velocity have kind of meant the same thing, but when you take the derivative of a position function, it gives you the velocity, which has a little bit more information baked into it than just the speed. When we say speed, we mean just the number, like the 50 miles per hour. Velocity is always going to contain some sort of directional information. And for us in this class, that's going to be either that it's a positive 50 miles an hour or a negative 50 miles an hour. So when your velocity is positive, that means that you're either moving forward or you're moving upward. Like if we're going to drive a car forward or we're going to throw a ball up into the air, those would be positive velocities. When you have a negative velocity, that means you're either driving your car in reverse or the ball is now falling, so going backwards or down. The speed in either case is going to just be the number, 50 miles an hour. Velocity is either going to be positive or negative, indicating either forward and up for positive or backwards or down for negative. So we're going to say that the speed of the object is going to be the absolute value of the velocity. The last thing we want to talk about in this section as relates to position and derivatives is acceleration. So let's think about what we've done so far with derivatives. So we have a position function, and let's say just for an example, we're going to talk about the position of a rock that you're dropping off of a tall 100-foot cliff. All right, so our position function would just tell you at any given time how far the rock has fallen down from the top of the cliff. So maybe this would be measured in units of feet. And we know that when we take the derivative of that, we get the velocity function. And that would tell us at any given time what our velocity is, our feet per second. And we know now that that velocity is going to be negative if we got a rock falling down. A downward velocity would be a negative velocity, but it would be in feet per second. Now, if I go and take a second derivative, so s double prime of t, that's going to tell me how fast the velocity is changing, right? So when we took the first derivative, we went from feet to feet per second. Now, when I take the second derivative, that's going to tell me how fast the velocity is changing. So it happens to be when you're dropping something, when gravity is pulling on it, that gravity will add 32 feet per second to the velocity of that object every second. So every second, the velocity increases by another 32 feet per second. All right, so this is going to tell you how many feet per second you're adding on every second. So how fast your velocity is increasing, right? And that's called our acceleration. And again, if you think in a car, the gas pedal is sometimes called the accelerator because when you push down on the accelerator, it changes the velocity. It changes how many miles per hour you're tacking on to your speed at each given moment. All right, so this is our acceleration. And typically we write this as feet per second squared, feet per second, rather than writing that rather complicated looking fraction I had before. So the acceleration of our object at time t is going to be given by the second derivative of the original position function, and we use a of t to represent the acceleration function. All right, so let's investigate these derivative quantities with a pretty simple example. We have a ball thrown upward with an initial velocity of 25 feet per second from a treehouse 15 feet above ground. Its height above ground t seconds later is given by the function s of t equals negative 16t squared plus 25t plus 15. And they've given us the position function for free here. We don't have to figure it out, but you can kind of see where some of the numbers in there come from. That 25 feet per second and the 15 feet, they do show up in the position function, and for good reason. But we just get to take the position function for free and run with it. So we're asked to find the velocity function and then v of 0.5 and v of 1.5. All right, so we're going to find our velocity function. Our v of t is going to be equal to the derivative of our position function. So I'm going to look up here at my position function and find its derivative. So derivative of negative 16t squared, I'm going to bring down that 2. It's going to make that a negative 32 t to the first. Derivative of 25t is 25. And then the derivative of 15 will just be 0. So that's our velocity function. And now they want us to find v of 0.5 and v of 1.5. So I'm going to come over and find v of 0.5. So we're just going to plug in negative 32 times 0.5 plus 25, and then we'll do the same thing for v of 1.5. All right, so let's ask our calculator to do these two calculations for us. All right, so negative 32 times 0.5 plus 25 gives me 9. And negative 32 times 1.5 plus 25 gives me negative 23. We always want to put units on our answers to word problems. So both of these answers are velocities. So their units are going to be in distance per time. In this problem, that's going to be feet per second. So this is going to be feet per second and feet per second. All right, so this means I've thrown this ball up in the air. After a half a second, it's traveling with a velocity of 9 feet per second. Notice it started off with 25 feet per second. Gravity is slowing that down, but at a half second, it's still moving upward. So remember, positive velocity means upward trajectory. Then at 1.5 seconds, its velocity is negative 23 feet per second. So that means at 1.5 seconds, we're already on the downward part of this trajectory. The ball's been thrown up in the air, gravity's pulling on it, it turned it around at some point, and now it's headed down in the negative velocity direction. We should also mention speed. These are both velocity values. So the speed at a half second would be equal to 9 feet per second, same units. But the speed at 1.5 seconds, remember, is just the number. We would say just 23 feet per second. All right, so speed does not report direction at all. Velocity is the one that has the positive or negative indicating direction. Second question they ask with the same setup, let's find our acceleration function. So remember that our velocity function was negative 32t plus 25. Our acceleration function is just going to be the derivative of that. It's going to be the derivative of negative 32t, which is negative 32. Derivative of 25 is just 0. All right, and there's those negative 32 feet per second squared that I mentioned earlier in the video. Anytime gravity is responsible for the acceleration, it's always going to be negative 32 feet per second squared. All right, so that's our acceleration function. And then they wanted us to find a of 0.5 and a of 1.5. And the acceleration function is really easy to plug into because there's no t to plug into. The acceleration function is a very boring function. It gives you the answer -32 no matter what question you ask it. So what's the acceleration at a half second? -32. Units are going to be feet per second squared. What's the acceleration at 1.5 seconds? -32 feet per second squared. And that's going to keep up until the ball eventually hits the ground.